Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to just picture the total energy output of our sun.
Oh, wow, starting big.
Right, but
Whoa.
I mean, really picture it. Not just, the warmth you feel on your face on a summer afternoon.
Yeah, that's just a tiny fraction.
Exactly. I'm talking about the sheer, just incomprehensible fusion reaction that's required to heat an entire solar system.
Constantly.
Right, constantly. Every single second. I mean, the sun has been burning steadily for, about 4.5 billion years?
Yeah, give or take a few 100 million.
And it has enough fuel to keep going for roughly another 5 billion years, right?
Yeah.
Okay, so imagine taking every last drop of that energy, the absolute sum total of a 10 billion year stellar lifespan.
The entire tank of gas.
Yes, and then detonating it all at once.
Yeah.
In a fraction of a single second.
It's almost impossible to actually visualize that.
It really is. But today, we are launching into an exploration of exactly that, one of the most violent anomalies ever recorded in space.
It's a wild one.
We're going to figure out why an explosion that basically broke every law of stellar physics has astronomers completely, rethinking the cosmic food chain.
It really threw everyone for a loop.
It did. So our mission today is to tear apart the data behind an event called GRB 25702b. And we're going to hunt down a prime suspect that has eluded astrophysicists for half a century.
And when we talk about this scale of violence, I mean, it really challenges the limits of our mathematical models.
It's off the charts.
Totally.
Right.
When we talk about a gamma ray burst or, a GRB, we are not just talking about a big explosion.
Right.
We are talking about the single most energetic, luminous electromagnetic events occurring in the universe since the Big Bang itself.
Like nothing else comes close.
Nothing. And the fundamental foundational rule of a gamma ray burst, a rule we've relied on since the very first ones were detected by those old Villa military satellites back in the late 60s.
Right, the ones looking for nuclear tests.
Exactly. But the foundational rule they established is brevity. They are fleeting.
They are the ultimate one-and-done cosmic events.
Yes. Out of the roughly 15,000 bursts we have cataloged over the last 50 years, the vast majority are over before you can even consciously register them.
Like a blink of an eye.
Faster, actually. A short burst might last a few milliseconds.
Wow.
And even a long burst, which is driven by what we call the collapsor model, that might last a couple of minutes at the absolute extreme.
But the fuel source is exhausted almost instantly.
Always. The engine turns on, burns everything, and dies.
But that entire framework completely collapsed on July 2, 2025.
It really did.
NASA's Fermi Gamma Ray Space Telescope triggers an alert for this GRB 25002b. And instead of flashing and fading into the background radiation like it's supposed to, the alarm just kept ringing.
It didn't stop.
It didn't stop for 7 hours.
Which is just, the duration alone sent shockwaves through the astrophysics community. To have a burst persist for 7 hours is statistically off the charts.
Impossible.
Right. But the continuous duration wasn't even the most baffling part of the telemetry.
Oh, yeah, the light curve data.
Exactly. The data showed that this event fired off 3 completely distinct massive bursts of gamma radiation spread out across an entire 24-hour period.
Which is just insane to think about.
And when the high-energy emission finally ceased, it left behind this multi-wavelength afterglow.
Like visible in X-ray, optical, and radio bands, right?
Yeah, all of them. And that lingering afterglow lasted for months.
Okay, let's unpack this, because the contrast here is the crux of the entire mystery.
It is.
If your standard gamma ray burst is like a single devastating camera flash going off in a pitch black stadium,
Right.
then GRB 2500702b was like someone firing up a massive industrial strobe light, leaving it running all day long, and like burning the bulb permanently into your retina.
That is actually a terrifyingly accurate analogy.
It sounds horrifying. And to really grasp why those 3 distinct pulses over 24 hours threw the whole astronomical community into chaos, we have to look at the engines that normally drive these bursts.
Right. The usual stuff.
Historically, we rely on 2 primary mechanisms. I'll take the first one, which is neutron-star mergers.
Okay, go for it.
So when 2 neutron stars in a binary system lose orbital energy via gravitational waves, they They spiral inward toward each other.
Getting closer and closer.
Right. And when they finally cross the threshold and collide, the sheer kinetic and gravitational energy of that merger powers a massive, short-lived relativistic jet.
Yeah, often resulting in an object that breaches the Tolman-Oppenheimer-Volkoff limit and collapses into a black hole.
Right. So that's engine number one.
And the second established engine is the collapser model. This is the one that drives the longer bursts.
The ones that last a couple of minutes.
Exactly. This requires a massive, rapidly rotating Wolf-Rayet star.
A huge star.
Huge. When its core exhausts its nuclear fuel, electron degeneracy pressure fails, and the core instantly collapses into a black hole.
Just boom, falls inward.
Right. The outer layers of the star then free fall inward, creating a dense, superheated accretion disk around that new black hole.
And that disk is what powers the jet.
Yes, the intense magnetic fields channel a fraction of that infalling material into twin jets that just punch their way out through the star's outer envelope at near light speed.
But, and here is the massive problem, both the merger model and the collapser model share a glaring limitation when you try to apply them to this July 2025 event.
A huge limitation.
They are terminal, absolute, irreversible endings. You can't merge the same two neutron stars twice.
Let alone 3 times.
Exactly, let alone 3 times. And once a massive star undergoes core collapse, you can't magically reinflate the stellar envelope just to crush it again a few hours later.
You really can't. The physics of a terminal event simply cannot support a 24-hour stuttering explosion.
It's one and done.
Right. The structural integrity of the progenitor is permanently destroyed in milliseconds in both of those scenarios.
So the scientists must have been losing their minds.
Oh, they were. When the Fermi data was published, the immediate reaction among theoreticians was this weird mix of intense fascination and complete bewilderment.
Like, what are we even looking at?
Exactly. I mean, one of the lead investigators on the detection team flatly stated, and I quote, "This is certainly an outburst unlike any other we've seen in the past 50 years.
That's a huge statement from an astronomer.
It is, because it implied an engine that could generate apocalyptic amounts of energy, shut down, and turn back on again with terrifying regularity.
Which means the traditional standard candles and stellar death models had to be thrown completely out the window for this specific event.
Into the trash.
Astronomers had to start searching for an engine capable of tearing an immense amount of matter apart systematically, piece by piece, rather than destroying it all in a single terminal cataclysm.
Yes, a totally different kind of machine.
And that search leads us to the primary suspect. A suspect that addresses a glaring, almost uncomfortable void in our mapping of the universe.
And what's fascinating here is how the physical evidence from this unprecedented burst aligns perfectly with the theoretical object we have been hunting for decades. To really contextualize this suspect, we need to take a step back and look at the mass distribution of black holes.
The black hole scale.
Right. At the lower end of the mass spectrum, we have stellar mass black holes.
These are the common ones, right?
Relatively speaking, yeah. These are the direct remnants of the massive star collapses we just discussed.
Okay.
They typically range from about 3 to perhaps 50 times the mass of our sun. And they populate the galactic disk in the millions.
Millions of them.
Millions.
Okay, so that's the small end. And at the absolute opposite extreme, we have the supermassive black holes.
The real monsters.
The gravitational titans anchoring the centers of virtually every large galaxy in the universe.
Including Sagittarius A star in our own Milky Way.
Right. And here we are talking about singularities that pack the mass of millions or even tens of billions of suns into a space smaller than our solar system.
It's hard to even wrap your head around that density.
It really is. So you have the small ones and you have the supermassive ones.
But between those two extremes lies the missing population.
The gap in the data.
Exactly. Intermediate mass black holes, or IMBHs.
Right.
Mathematically, they absolutely must exist.
Because the big ones had to come from somewhere, right?
Precisely. The hierarchical merging models of galaxy formation suggest that supermassive black holes didn't just, spring into existence fully formed.
It had to grow.
They had to grow by consuming smaller black holes. So IMBHs, which range from a few hundred to 100,000 solar masses, are the required evolutionary stepping stones.
They're the missing link.
Exactly. Furthermore, models of the early universe suggest that massive, pristine gas clouds could have undergone direct collapse into IMBH seeds.
So the math actually demands their existence. We should theoretically be tripping over these things in certain galactic environments.
We really should.
Yet observational astronomy has a notoriously difficult time finding them.
It's been incredibly frustrating.
I mean, it's the equivalent of paleontologists finding fossil evidence of millions of house cats and thousands of giant T-Rexes, but never finding a single skeleton of a wolf or a bear.
That is a perfect way to put it.
The entire middle of the mass distribution is essentially a ghost town.
Just completely empty.
Why? I mean, why is an object weighing 50,000 suns so incredibly difficult to detect?
It comes down to their environment and their accretion rates.
Okay, break that down for us.
So a black hole is, by definition, a region of space-time where gravity prevents light from escaping.
So they're inherently invisible.
Right. The only way we ever detect them is through their interaction with surrounding matter.
Specifically, when they feed.
Exactly. When they eat, they get messy, and we can see the mess. Supermassive black holes sit in the dense, chaotic environment of a galactic core,
Lots of food there.
a near-infinite buffet of interstellar gas and wandering stars. This creates massive, brilliantly luminous accretion disks and active galactic nuclei.
So they shine incredibly bright because of all the friction.
Yes. And on the other end, stellar mass black holes are often found in tight binary systems.
With a partner star.
Right. And they are continuously siphoning plasma off that companion star, which generates a steady stream of detectable X-rays.
So they're messy eaters in crowded rooms, which makes them visible.
That's a great way to put it.
But an intermediate mass black hole doesn't have those advantages.
It really doesn't.
Yeah.
They are too massive to maintain a tight, stable binary orbit with a standard star without just completely disrupting it.
They're too bulky.
Yeah. And dynamic friction models suggest many of them actually get kicked out of the galactic core during early merger events.
Yeah, kicked out, like ejected.
Yeah, gravitational slingshots basically fling them outward. So they are relegated to the galactic halo or the outer disk.
The suburbs.
They're wandering through the vast, empty suburbs of the galaxy.
Where there's nothing to eat.
Exactly. The ambient interstellar gas density in these regions is incredibly low.
So they're just starving.
Basically, yeah.
Yeah.
If you look at the Bondi-Hoyle-Littleton accretion rate,
Which is what exactly?
yeah, it's the formula that dictates how much ambient gas a black hole can passively sweep up just as it moves through space.
Okay.
According to that rate, an IMBH in the galactic suburbs is capturing almost nothing.
Wow.
It has no accretion disk. It emits no X-rays. It is just a silent, invisible, gravitational sinkhole drifting through the dark.
Drifting until its trajectory intersects with something massive enough to light up that dark.
Precisely.
So an intermediate mass black hole solves the problem of why the suspect was hiding from our telescopes.
It fits the profile.
But a quiet, starving black hole doesn't spontaneously generate a 7-hour multi-stage gamma ray burst.
No, it doesn't.
It required a catalyst. It required a victim to cross its path.
Yes, it did.
And that brings us to the specific mechanics proposed by these researchers. They didn't just point a finger at an IMBH, they modeled the exact crime scene.
They really did. They introduced this concept called the millitidal disruption event model.
Millitidal disruption event.
Okay.
SECI.
Right. And in this highly specific scenario, the catalyst, the victim, was a main sequence star.
So just a regular, stable, hydrogen-burning star, very much like our own sun.
Just an ordinary star minding its own business. But through sheer cosmic bad luck, the dynamic orbital interactions within its local star cluster perturbed its trajectory.
It got nudged.
It got nudged, sending it on a path that brushed dangerously close to the gravitational sphere of influence of a lurking intermediate mass black hole.
Now, when a star encounters a black hole, we often hear the term spaghettification, which is, a fun word for a truly horrifying process.
Very fun word. Terrible way to go.
Right. But to understand how this specific event generated gamma rays, we need to go beyond the basic definition of getting stretched out. We need to look at the gravitational gradient and something called the Roche limit.
Ah, yes, the Roche limit. So this is the critical distance at which the tidal forces exerted by a massive body, in this case the black hole,
Right.
exceed the gravitational forces holding the smaller body, the star, together.
So it's the point of no return for the star's structural integrity.
Exactly. As the star approaches the black hole, the gravitational pull on the star's leading hemisphere, the side facing the black hole, is significantly stronger than the pull on its trailing hemisphere.
Because gravity gets exponentially stronger the closer you get.
Right, so the front is being pulled so much faster than the back, the star is literally stretched apart.
Wait, hold on. Here's where it gets really interesting and where I have to just interrupt the standard tidal disruption model.
Go for it.
If the star crosses the Roche limit and the tidal shear forces overcome its self-gravity, the star is ripped apart into a stream of superheated plasma.
Yes, shredded.
Half of that material gets ejected out into the interstellar medium, and the other half circularizes into an accretion disk around the black hole.
The buffet opens.
Right. The black hole feeds, and through the Blanford-Znajic process, the twisting of magnetic field lines in the ergosphere acts as an immense particle accelerator,
Blasting a relativistic jet toward Earth.
Okay, so that perfectly explains a massive burst of energy.
It does.
But you just said the star is ripped apart.
I did.
If the progenitor is shredded into a plasma stream, how does the Fermi telescope register 3 distinct bursts over 24 hours? The math just doesn't add up.
It really doesn't seem to.
You cannot cross the Roche limit and suffer complete structural failure 3 times.
You are absolutely correct, and that is the exact physical contradiction that the team had to solve.
Because you can't eat the same star 3 times.
Right. A standard tidal disruption event, or TDE, involves a deep plunge, where the periapsis, which is the closest point of the orbit, is well inside the Roche limit.
So it dives deep into the danger zone.
Deep in. And in that standard scenario, total disruption is instantaneous. The engine turns on once, feeds until the accretion disk is depleted, and then turns off.
Well, then done.
To get 3 distinct bursts, the team had to calculate a scenario where the victim actually survives the initial encounter.
Surviving the first bite.
Surviving the first bite.
This completely shifts the mechanics of the whole event. It requires an incredibly precise orbital trajectory, doesn't it?
Oh, precision is staggering. It requires a grazing encounter.
The grazing encounter.
The researchers modeled a highly elliptical, near parabolic orbit. So the star's periapsis didn't plunge deep into the Roche limit. It just barely skimmed the edge of it.
Think of it like skipping a stone across the surface of a pond.
Yes.
The stone doesn't just plunge straight down to the bottom on the first impact. It hits the dense surface of the water, experiences intense drag, loses a fraction of its kinetic energy, and bounces back up into the air.
Exactly.
But because it lost energy, its next arc is shorter, bringing it back down for a second, more damaging impact.
That mechanical analogy maps perfectly onto the hydrodynamics of this event.
So how does that look for the star?
On the star's first close approach, the tidal shear forces were only strong enough to strip away the outermost layers of the star's gaseous envelope.
Just skimming off the surface.
Right. The dense stellar core, where the self-gravity is strongest, remained entirely intact.
So the black hole shears off a massive chunk of hydrogen plasma.
Yes.
That stolen material falls into the gravitational well, circularizes, and triggers a violent accretion episode.
The first meal.
The magnetic fields wind up, the relativistic jet punches outward, and Fermi's detectors light up with the first burst.
Boom. Burst number 1.
But the black hole hasn't destroyed the engine. It has only taken a surface layer.
Precisely. After that first grazing pass, the surviving stellar core swings back out to the apoapsis of its elliptical orbit.
Flying back out into space.
But just like your skipping stone, the encounter robbed the star of critical orbital energy and angular momentum.
It's slowing down.
It cannot escape the black hole's gravity. Its orbit is decaying rapidly.
The star is bleeding out, and it's being pulled back in for a second pass.
It is. Several hours later, dictated purely by Keplerian orbital mechanics, the damaged star swings back down to periapsis.
For round 2.
Because its orbit decayed, this second pass takes it slightly deeper into the Roche limit.
Oh, no.
The tidal forces are even stronger this time. A much larger fraction of the star's mass is violently torn away.
So the second massive chunk of plasma hits the accretion disk.
Exactly.
The temperature and magnetic flux spike again. The black hole fires a second relativistic jet, and Fermi records burst number 2.
And the star, now critically deformed and lacking the mass to maintain its structural integrity at all, swings out one final time on a drastically shortened orbit.
It's barely holding together.
When it returns for the third pass, it finally plunges deeply enough into the Roche limit that total disruption occurs.
The final blow.
The remaining core is entirely shredded, The black hole consumes the bulk of the stellar mass in one final catastrophic feeding frenzy.
Generating the third most sustained gamma-ray burst.
Exactly, the big one.
And then the leftover debris from that final total disruption circularizes into a massive, stable accretion disk, which slowly drains into the black hole over the following weeks.
Which perfectly explains the months-long X-ray and optical afterglow we observed.
So the partial stripping model doesn't just explain the mechanism, it explains the exact temporal spacing of the data.
It's beautiful. The timing of the bursts is a direct readout of the star's decaying orbital period.
That's amazing.
It is a stunning piece of theoretical physics because it takes a completely anomalous light curve and maps it flawlessly onto the gravitational mechanics of an intermediate mass black hole slowly wearing down a main sequence star.
It's just a brilliant deduction. But, theoretical mechanics and temporal alignment are really only two legs of the stool.
True.
If you want to definitively place a suspect at the scene of the crime, you need location data.
You need to know where it happened.
Exactly. Does the physical location of GRB 250702b actually support the presence of a wandering intermediate mass black hole?
If we connect this to the bigger picture of galactic architecture, the location is perhaps the most compelling piece of evidence. Oh yeah, through rigorous multi-wavelength follow-up observations, astronomers were able to pinpoint the exact coordinates of the burst.
Okay, where was it?
The explosion originated approximately 5.7 kiloparsecs from the dynamic center of its host galaxy.
Okay, 5.7 kiloparsecs. Let's put that spatial measurement into perspective. A single parsec is about 3.26 light years.
Right.
So 5.7 kiloparsecs is roughly 18,500 light years away from the galactic core.
It's a massive distance.
It is. If you look at the structure of a typical spiral galaxy, the core, the central bulge, is an incredibly dense, chaotic environment packed with ancient stars, molecular gas clouds, and of course the central supermassive black hole.
And 5.7 kiloparsecs outward places this event entirely outside that central hub.
It's way out there.
It places it firmly in the outer galactic disk or even the stellar halo. In galactic terms, this is the remote countryside.
The deep suburbs.
The stellar density out there is just a fraction of what it is in the core.
So why does that specific remote location serve as the smoking gun for an intermediate mass black hole?
Because of the dynamics of black hole formation and migration.
Okay.
If an explosion of this magnitude had occurred directly in the galactic center, the immediate logical conclusion would simply be that the central supermassive black hole had consumed a star.
Because they do that all the time.
Right. The immense gravity of a supermassive black hole easily powers tidal disruption events.
Makes sense.
Conversely, if the burst had occurred within a dense, active star-forming region in the spiral arms, you could potentially argue for a highly anomalous core collapse of a massive Wolf-Rayet star.
Because that's where the massive short-lived stars are born and die.
Exactly. But GRB 250702b happened in a region where neither of those extreme engines should logically exist.
Ah, I see.
A supermassive black hole cannot wander 18,500 light years from the center of its galaxy without taking the entire galactic structure with it.
It would drag the whole galaxy along.
It would ruin everything. And massive Wolf-Rayet stars have incredibly short lifespans, only a few million years.
So they don't have time to travel.
Right. They rarely have the time to migrate out into the sparse galactic halo before going supernova.
So you've eliminated the giant black holes and the giant stars based purely on zip code.
Exactly. The only object capable of generating a relativistic jet of this magnitude, while simultaneously possessing the gravitational subtlety to partially strip a star over 24 hours and existing in the low-density outskirts of a galaxy.
Is an intermediate mass black hole?
Yes. They are theoretically predicted to inhabit globular clusters, which are these dense, ancient spherical collections of stars that orbit in the galactic halo.
Wow.
A wandering IMBH inside a globular cluster, located 5.7 kiloparsecs from the core, is the exact profile required to execute this event.
The location, the weapon, and the timeline all converge on a single invisible suspect.
It's a very tight case.
It really is. But, to maintain the rigor of this discussion, we have to look at the pushback from the broader astrophysics community.
Oh, absolutely. Science is all about pushback.
Right, because as elegant as the milli-TDE model is, it is not the only theory attempting to explain the 24-hour stuttering of this event.
No, it's not.
What are the competing models that other astronomers are throwing into the ring?
Well, the scientific method requires rigorous opposition, and several alternative theories have been proposed to explain the anomalous light curve without invoking a rare IMBH encounter.
Okay, what's the strongest alternative?
One of the primary competing models involves a highly magnetized magnetar.
A magnetar, meaning a type of neutron star with a magnetic field billions of times stronger than anything on Earth.
Correct. In this model, the progenitor is still a massive star collapse. But the remnant left behind isn't a black hole, it's a rapidly spinning magnetar.
Right, so a giant star dies, leaves a supermagnetic core.
Yes. And the theory suggests that as the stellar envelope collapses, some of the material has too much angular momentum to fall directly onto the magnetar, forming a fallback accretion disk.
So instead of a clean jet, the magnetar is basically choking on the fallback material.
Exactly. The extreme magnetic fields of the magnetar interact violently with the clumpy, irregular fallback disk.
Like a jammed engine.
Yeah. As dense clumps of matter overcome the magnetic centrifugal barrier and crash onto the magnetar's surface, they trigger massive magnetic reconnection events.
Which are what, essentially?
Essentially universe-shaking stellar flares. The 3 distinct pulses observed by Fermi could, theoretically, be 3 exceptionally large clumps of fallback material striking the magnetar over a 24-hour period.
That's a fascinating alternative because it relies on known existing stellar remnants rather than requiring the discovery of a missing IMBH.
Right. It uses physics we already have confirmed.
But does the magnetar model fully explain the raw energetics of the burst? I mean, this was a massive explosion.
And that is where the debate gets incredibly heated.
I bet.
Magnetars are powerful, but their energy budget is strictly limited by their rotational kinetic energy and their magnetic field strength.
They only have so much juice.
Exactly. Generating a 7-hour continuous gamma-ray burst, punctuated by 3 massive relativistic pulses, pushes the absolute theoretical limits of what a magnetar can physically produce before it spins down and exhausts its energy.
It's like running your car at the red line for 7 hours straight.
Yeah, many physicists argue the energy output of 250702b is simply too high for a neutron star remnant to handle without breaking down.
Okay, so the magnetar is a stretch energetically. There's also the precessing jet model, right?
Yes, the geometric model.
This is the idea that the engine itself isn't turning on and off, but our perspective of it is shifting.
Correct. So in a standard collapsar event, the black hole fires a continuous relativistic jet.
A single solid beam.
Right. But if the accretion disk is significantly misaligned with the spin axis of the black hole, a phenomenon called lens-thirring precession occurs.
Okay, walk us through that.
The immense frame-dragging effect of the spinning black hole actually forces the accretion disk and consequently the jet itself to wobble like a dying spinning top.
Okay, so the black hole is firing a single continuous 7-hour beam of energy into space.
Yes.
But because of the wobble, that beam is sweeping across the cosmos like a lighthouse.
Sweeping around in a big circle.
And the Fermi telescope only registers a burst when that narrow beam directly crosses our line of sight.
The wobble brings the jet into our view, sweeps it away, brings it back, and sweeps it away again.
It's a purely geometric explanation for the 3 pulses.
Exactly. The engine never stopped. It just wasn't pointing at us the whole time.
That is a brilliant application of general relativity.
It's very clever.
But again, it runs into the duration problem, doesn't it?
It does.
A standard collapsar jet exhausts its accretion disk in minutes. To have a continuous jet wobble for 7 hours requires an impossibly massive, sustained fuel source.
Which circles us right back to the necessity of something much larger than a standard star.
It circles us right back to the immense gravitational well and extended feeding time of an intermediate mass black hole tearing apart a main sequence star.
It really does. This raises an important question about how we observe the universe. Every competing model requires stretching existing physics to the absolute breaking point.
Yeah, you have to force the puzzle pieces to fit.
But the Millet-TDE model, while requiring an elusive IMBH, elegantly answers the energetics, the timing, and the location without breaking the laws of thermodynamics or orbital mechanics.
It just fits naturally.
It fits beautifully.
So what does this all mean for you, the person just looking up at the night sky?
It's a big deal.
When we strip away the competing models and the complex hydrodynamics, what are the actual stakes of this specific July 2025 event?
If the interpretation presented by these researchers survives the gauntlet of peer review and competing theories, the stakes are monumental.
History-making, really?
Yes. GRB 250702b will be recorded as the first time in human history that we have conclusively witnessed an intermediate mass black hole in the act of feeding.
The first confirmed sighting.
It moves a purely mathematical concept the missing link of galactic evolution out of the realm of theoretical equations and into verified, observable reality.
It bridges the evolutionary gap. It finally proves that the universe does build black holes in the middleweight division.
Yes.
And that they are out there, quietly shaping the dynamics of the galactic halo.
It would easily be categorized as one of the most significant astronomical discoveries of the decade.
Without a doubt.
Fundamentally altering our understanding of black hole demographics and the dangers lurking in those globular clusters.
And it serves as a powerful reminder of how science actually progresses.
It's never a straight line.
No, it's not. The most paradigm-shifting discoveries don't usually arrive with a neat little bow, just confirming what we already know.
Usually it's someone saying, well, that's weird.
Exactly. They arrive unannounced, disguised as a massive, screaming anomaly that completely breaks our existing rules. A 7-hour stuttering explosion that nobody can immediately explain is exactly the kind of friction that forces astrophysics to evolve.
It forces us to look into the vast, seemingly empty spaces where we assumed nothing of consequence was happening.
And realize that the dark is actually heavily populated.
Very populated.
Which leaves me with a final lingering thought that I frankly find a little deeply unsettling.
Oh boy, here we go.
Well, we have established that an intermediate mass black hole, a singularity weighing tens of thousands of times more than our sun, can lurk completely undetected in the quiet suburbs of a galaxy.
Yes, it can.
It emits no light, it makes no sound, and it remains totally invisible until a star just happens to wander a fraction of an astronomical unit too close.
Just a silent trap.
It makes you wonder. When you look up at the Milky Way tonight, past the dense, glowing core and out into the sparse, quiet halo of our own galaxy, how many of these invisible, silent giants are drifting through our very own cosmic suburbs right now, just waiting in the dark?
Well, that is the exact question that will be keeping astronomers glued to their telemetry data tonight. The missing monsters are finally making themselves known.
Well, on that awe-inspiring, slightly terrifying note, we're going to wrap up this exploration of GRB 250702b.
It's been a wild ride.
Thank you so much for joining us on this intellectual journey today, and for stepping out into the cosmic dark to unpack the universe's greatest mysteries with us. Keep looking up, and we'll catch you next time.